there should be an option of going to full screen participants list and all. So in order to go to full screen, I guess there was an option for going to full screen and hiding this participants panel. Um, yeah, here this full screen or not full screen. There should be. I'm just looking for the full screen option. You can. I think you will have to check. Sambhav, you will have to check whether from your side you are able to see full screen option. Is there any option for going full screen? Because here in the recording, it will record my screen and I don't.
I'm not getting any option, any such option, sir.
Feel. So there was an option, maybe view more rooms, settings. Anyway, we will look at it later. There is an option of going full screen. Somehow, right now I'm not able to recall. So go ahead and describe whatever you have been able to do. So this is your 65 nanometer or 45 nanometer. Which node, which model did you use?
So I use the 45 nanometer, but and the length is 65 nanometer for the MOSFETs.
Okay, so in 45 nanometer, you can go for minimum channel length as 45
For
nanometer. So in any technology, if it is a 45 nanometer technology, you can go to channel length down to say uh, 45 nanometer, whatever is the technology node. W can be larger. So those things we will discuss when we discuss the scalability of MOSFETs and the scaling of the MOSFET devices, current technology nodes. MOSFET structures also have changed. So those things we will briefly discuss. But go ahead and show the setup what you have done.
so I use the VDD as 1 volt, and then for the input I gave a pulse
Just
of
show the sources, the components that you have brought. Just double click the components so that everybody can see which components have been used.
this has been used.
The VDD and the input source. Just show the components, what parameters we have entered for the components. Just click on it.
So for the VDD I used 1 volt. Is visible, I guess.
Yes. So where do you see the enter the parameter? Show the parameters. How are you entering the parameter?
Here, and then for the MOSFETs.
No, in the VDD and the pulse source that you have put, show the
Okay,
parameters, how you have entered the parameters.
these are the parameters.
So here you can see these are different options for the source. So pulse, sinusoid, uh, piecewise linear is when you are having a data table from where you can generate the source. But if you choose the pulse source, as he has done in this case, you can go to the parameter window. Why did you close it? Just open that window. The parameter window for the V1. So here you can see all the again closed. So I ask you to keep it open, please.
It is open, sir.
I'm not able to see it. So the parameter window is not visible. So maybe you can maximize this lower schematic. The schematic window you can maximize, hide the simulation waveform. Now open that window. Yes, so here you can see the parameters. The initial voltage V, initial V on, that means what is the high level that is given. Delay is 0. Right now you don't have any delay included in the waveform, so it will start from t equal to 0. And rise time for time 50 picosecond, and the duration of t on, that means the pulse width is 0.5 nanosecond. Okay. So is there any other parameter, or can you scroll down?
No more parameters, sir. These are the parameters.
And do it for the V2. Just click the V2 also. So this is which source you have chosen. You have chosen a DC source. Like how did you select V2? Just show how did you instantiate V2?
I chose a DC source, sir. Just I
Yes. So
tapped.
show how did you select. So from the select component, you have this DC source, and click on it and just show how the parameter is entered. That those who are not comfortable, they can.
Here we can enter the DC value we want.
I think we're not able to see the full screen. So V3, where is the entry? Like we are just showing the V3. I'm not able to see the text box, the box where you can enter the value.
Is it visible now, sir?
Yes, I think there was some disruption on my side. You are able to hear me now again?
Yes, sir.
Yes. So just uh, so likewise, you have to connect all these parameters. Just show the MOSFET. How did you enter the parameters model file? So here the DC value is given. Likewise for the MOSFET, in the tutorial also it was mentioned how to include. So here the parameters you can enter, and likewise the model file path also you can provide. So he is using the 45 nanometer model file that was the link for which was posted earlier. So now you can run the simulation once again, generate the waveform, and show the simulation setting, what simulation you are choosing, the transient simulation, how you have chosen the setup. So somehow it seems like the
I
whole
used.
window is not coming. We are not able to see the entire dialog box. So some part is getting cut. Only partially we are able to see. But anyway, so you can uh, remove this extra source that you have put, V3.
Sir, removed.
Yes, you can show the trans simulation setting. So here dot tran 10 you have entered, but the control panel we are yeah. So everybody is able to see. I think there is some problem in the display. We are not able to see the entire dialog box. So it is getting only some corner is visible. But uh, I'm not sure what is the display issue. But in this particular dialog box, the simulation can be chosen transient AC, DC, and you can for transient analysis you can set up the simulation time. Likewise, AC and DC analysis also can be done. Those who have used it earlier, they may be familiar. Those who have not, this is the panel on which you can set up the simulation parameters. So close it and run. So this is output waveform, and the input we cannot see, so you can plot both of them. So now input and output both are visible. And what about the current? So have you plotted the currents of the PMOS and NMOS? And the NMOS.
These are the currents, sir.
Yes. So now you can see the PMOS and the NMOS current. Plot the waveform also, the input waveform as well. Yes. So can you zoom into one of the waveform, just expand it just so that only one or the just two of the pulses are visible? Make at least two pulses visible. Not this way. We want the pulses also to be visible. So the rising edge and falling edge. So the pulse waveform, can you make the color yellow or something so that it is more visible? Click on that pulse waveform, change it to yellow. So here we can see, yes. So here we can see the input waveform is plotted and the NMOS and PMOS currents are also plotted. So the green one is the NMOS current and the red one is the PMOS current. That's what we discussed towards the end in the last lecture. And here we see that ideally, of course, as we discussed, the NMOS current should be coming at what point? When the input is going high, because at that point NMOS will be turning on and discharging the output. So we are getting the big peak in the NMOS current when the input is turning high. And the big peak in the PMOS current is coming when the input is going low. So we can see the red peak is high when the input is going low. But there is a small green peak along with the red peak. Along with the red, big red peak, there is a small green peak coming. And likewise, if you just click on the red waveform, yeah. So we look at the red waveform. There also you can see when the green pulse is coming, where the green peak is coming. There also there is a non-zero red current. That means the PMOS current also visible. So now here, if you reduce the rise time fall time, so what you do is now you reduce the rise time to say 5 picosecond. In the parameters, you just change the rise time fall time to 5 picosecond. So ideally, we would expect that when the PMOS current is coming, there should be no NMOS current, and NMOS current is coming, there should be no PMOS current. But we see that when the big red peak is coming, there is a small NMOS current also. There is a small green peak also. So why that is happening?
Sir,
Yes.
hello. Sir, like when we have the rise time or the rising edge or the falling edge, then suppose that initially the input was low. So when the input was low, then our PMOS was on and the NMOS was off. Now, as slowly the input voltage rises from the low to high, then my PMOS gradually, the gate voltage of my PMOS gradually increases and gate voltage of NMOS also increases. So what happens is that the NMOS now sees itself into saturation and the PMOS slowly comes from triode to saturation and then to cutoff. So a time comes in the middle where both the PMOS and NMOS are simultaneously on. And at a particular time, both are in saturation also. So that's why we get a peak for both the PMOS current and the NMOS current, even at the middle, like at T by 2 time
Yes.
periods also.
So that is the correct explanation. So when the voltage is close to midway, then both of them are, turning on, because when the input is completely VDD, PMOS is off, NMOS is strongly on. And when the input is completely zero, PMOS is strongly on, NMOS is off. But when it is midway, then you still have VGS of NMOS, say, VT maybe around, say, a zero 0.4 volt. And the midway value of the input is around 0.5 volt in this case, because supply voltage he has taken as 1 volt, and the pulse of the input is also 1 volt. So when it is, if the VT is suppose 0.3 volt or 0.4 volt, so VGS is still higher than VT for NMOS. Likewise, the VSG is going to be higher than mod VT. VSG for PMOS is going to be mod VT higher than mod VT for PMOS. As a result, both of them will be turning on simultaneously. And because both of them are turning on simultaneously, so there is going to be a small, current flowing through both of them directly going to ground. So ideally, we would expect that if the input rise time fall time is zero, a perfectly, step function, then at no point of time, NMOS and PMOS will be turning on together. That is the ideal concept of the CMOS circuit. At no point of time, there should be a static current flow between the PMOS and the NMOS. There should be no static current path between VDD and ground through PMOS and NMOS. But now, if you have a non-ideal input signal where it is gradually rising from 0 to VDD, which actually happens in real circuits, so then for a small duration, both NMOS, PMOS will be turning on and there will be a common, current flow. That's what it shows that, although you have the larger current coming in NMOS when the input is turning high and larger current coming in PMOS when the input is turning low, but both of them are conducting together for a small instance, and that leads to, non-zero current for the other transistor also. So now you can just experiment. You can just try to simulate it with a very small rise time, maybe just reduce it to 5 picosecond. We will see that additional peak that is coming, that may become small because now they are not getting much time to conduct together. So the NMOS PMOS overlap of the on period, that will be reduced. Again, plot the currents.
Sir, I have a
Yes.
question. Sir,
Yes.
why is there the current like in NMOS or in PMOS, like in the falling edge, I guess it was opposite sign, and in one case it was in NMOS was low and PMOS was high. So why is that happening?
Yes, so that is depending upon the overall current direction. So the way he is plotting the current, it is the source terminal current for the NMOS and for the PMOS, and for the NMOS, it is the drain region current. So if you look at the condition where we have the NMOS current, so in the transition period, ultimately, both the currents should be in the same direction, and there may be some negative current because of charge sharing. That part I will have to see, because if you are only talking about the static current flow or the short circuit current, that should be from VDD to ground. That means it should be positive in the PMOS and positive in the NMOS. But if there are some other current components because of charge sharing, and the capacitive coupling introduces some charge sharing that we have not discussed yet, that may lead to some additional component that I will discuss in the theory. So now
Sir,
at least you can.
will there be some negative currents because of the source to gate capacitance? Like it appears that
Yes,
some
so that
current
is
flow.
it's the CGS, and also the drain to body capacitances are there. So there may be some capacitive coupling because of that, and it may lead to some current flow from that node. So that may be responsible for the negative current. So when we discuss the parasitic behavior, we will discuss that. But you will see that the current magnitude, just look at the relative magnitude of the PMOS and MOS current. You can zoom into the edge. So there are two components. One is the static current flow and another one is the. Now here what we see is that the transient simulator, the time step is not small enough, because of which we are getting slightly cruder waveform. So in LT Spice, I think there is a you can just go to that simulation setup. You may have to increase the times, or the resolution of the time step needs to be increased so that we can simulate more accurately. So we need to check whether there is an option, because right now you are seeing that it is simulating much less accurately. It is having crude waveform. It is taking lesser number of points. So for transition region, because we have reduced the transition time, we need to simulate with higher time step resolution. That means the gap between two time steps should be much smaller than the rise time fall time. Then only we will get multiple points within that rise time and we will get proper results. If your simulation time step is comparable to the rise time fall time, then you will not get accurate behavior over there. So right now we need to see whether it is able to simulate with reduced resolution. So just go to the setup, the simulation setup. There should be a parameter called time step. Time step, is there any parameter? Maximum time step. Maximum time step, you can set it to say 0.1 picosecond or something. And total simulation time you can reduce maybe okay, 10 nanoseconds, let it be, just run. So if you reduce the if you reduce the time step, that means it will simulate more accurately. It will take more points within that small 5 picosecond window so that you get a more realistic waveform. Otherwise, it will simulate crudely. It will take very few points. You will not get the proper waveforms. So now again, zoom into one of the edges and see whether the waveform has improved, whether it is coming more realistic. So maybe some more points are coming. So you can here again you can see that the relative magnitude of the other current, the the second MOSFET's current is slightly reduced. So this is the falling edge. Here the PMOS current should be more and NMOS current should be lesser. So here we can see there is the second peak is slightly lesser. Likewise, go to the rising edge. Rising edge, falling we have already. So here, once again, we can see that the M2, which is the NMOS current is high because that is supposed to sink the current. PMOS is also showing some current, and that is in the negative direction. Now that negative direction current, what does that mean? That there is a current flowing in the opposite direction, and that is at the source. So at the source, what can lead to negative direction current? That means a current which is flowing out of the source. So that may be because of the gate to source coupling. So gate to source coupling, because there is a input voltage coming at the gate and it is sharply rising from 0 to VDD, there is a CGS, gate to source capacitance, which will lead to charge injection, or basically current coupling from the gate to source. Ideally, we can ignore the capacitance, but ultimately, if you look at the CGS, that will lead to a small signal current flow from gate to source, because now the input is transitioning fast. So if you look at the impedance of that CGS, for high frequency, it will allow some current to pass, right? And as a result, that high frequency component passes from gate to source, and it leads to current in the opposite direction. It appears as if the charge is getting injected from the source. That's why you are getting negative current, because the definition for the MOSFET current is downward going, it is positive into the source. But at that node, we are getting a negative current because of the capacitive coupling between the gate and the source. So that CGS factor will lead to that negative spike. Now, if you put a cap, so we had discussed that we need to stimulate with a capacitive load as well. So can you put an additional cap of, say, did I ask you in the assignment to put a cap? I guess yes. So I might have asked you to put an additional cap at the output of certain value, which can be, say, 50 femtofarad. If I missed it, please try to do that. So I put a cap of, say, 50 is too high. So let us put a cap of, say, 10 femtofarad. Put a ground. Now, what will happen if you are putting a cap? So right now, you just put 10 femtofarad. So what is expected? How the waveform should change if we are putting a 10 femtofarad cap? Anyone?
Sir, we'll get a slightly delay in the inverter characteristics, like the inverted waveform.
Slightly, okay. So delay is one thing. Apart from delay, anything else? So why the delay will come?
So because now we have a 10 femtofarad capacitor put across this, so the effective capacitance will be this capacitance combined with the other parasitic capacitance. So that will
Yes. So
increase the time.
yes. So
Constant
now
slightly.
at the output node, we have some additional capacitor that will lead to uh, overall load capacitor has increased. Earlier, only the parasitic capacitance of the device were contributing to the output node capacitor. Now we have additional 10 femtofarad capacitor. Now, in this technology, if I look at the parasitic capacitor that will come into picture, for 65 nanometer technology, if I look at the CGD, CDB, etc., that will be per micrometer. If I say it will be around 1 femtofarad, but now we are putting 10 femtofarad. So that means we are significantly increasing the load capacitance. So now, because you are having a larger capacitor, so it will take more time for the PMOS to charge that capacitor, and it will take more time for the NMOS to discharge that capacitor. So one answer is that yes, the delay will be more. What else? What else will change? Anything you think will change? Delay is one thing, definitely. What else? Yes, hello?
There will be a change in the bandwidth.
Bandwidth. In the simulation waveform, what else we expect? Bandwidth means maximum speed at which you can operate, right? So maximum speed that
Yes.
at which you can operate will depend upon what?
Sir, it will depend upon the dominant pole. So since we have a capacitance attached, so now the capacitance has changed. So there will be a change in the dominant pole.
All this pole zero analysis that we do, that is for analog circuits and analog signals, because they are small signal parameters, and the small signal, resistance, small signal capacitances, they determine the pole. In this case, it is a
So
large
one
signal
thing which
model.
will change.
So still
So one
the,
thing which will,
yes, hello?
so one thing which will change maybe is the current which was usually before spiking, like rapidly spiking and then falling, will not be that much of a spike, but it will take some time to retain and then it will fall.
Yes, because the capacitor is taking more time to charge, so definitely the current will also remain for longer time. That is
So some
true.
power consumption will be there. It is more power will be
Power
consumed.
consumption will definitely, what is the power consumption dependent upon? We have discussed yesterday. What was for CMOS? I think we did not derive the power consumption. I will do that. So here, that is a good point, but I'm talking about transient waveform. The power consumption will increase. Why will it increase?
So because now the static current, the current stays hold on for some time. Earlier it was just spiking and then falling down, but
So
now
why is the current staying longer?
so the current is staying longer because the capacitance, the RC time constant has now the RC
No,
time
talk
constant
in
is
terms of, if you're talking about power, you need to talk in terms of energy. So why the current is staying longer? How can you explain with respect to energy?
uh,
What is the energy dissipated in inverter? Yesterday we discussed about certain power consumption parameters, and I think the CMOS part I did not derive, and analog part only I looked at. So for this CMOS inverter, what will be the power consumption? How do we derive that? I think there is an option of annotation somewhere. Annotation, take control, something. Uh, yes. So who can answer? How do we derive the power consumption here? There is an annotation option. Where is that annotation option? Otherwise, I will have to share. So take control is not. I don't know whether take control will help. No, cancel. So there should be an annotation option which allows me to annotate. Uh,
Sir,
anyway.
maybe one way to do this may be that we write the current equation at times like when it is in saturation and the point where it is in triode. And then we know that the voltage across the capacitor is basically Q by C, and we know the current. So the current becomes C dV dt, and so we bring out some voltage as a function of time, and then we multiply with the current.
You
And
don't
then
need to do all of that. So if I ignore the energy dissipated because of the direct current path, which is coming for a short time, so assume that we ignore that. Assume that that direct current path between NMOS PMOS is on for a very short duration. If we ignore that, what is the energy dissipated in one cycle? When the capacitor is getting charged from 0 to VDD, what is the energy getting deposited, or what is energy lost from the VDD in charging that capacitor?
so the energy required to charge the capacitor is CV square. That part.
Half CV square, right? CV square is the energy, right? And then when that energy is that charge is again shunted to ground when the NMOS turns on, that energy has gone to from capacitor to ground, right? So that overall charge CV has traveled from where? VDD to ground. Capacitor was just an intermediate halt. So when the input become low, the VDD charged the capacitor through PMOS. But when the input became high, the NMOS discharged that capacitor. So finally, that charge came from VDD, went to ground. So the total charge that was deposited on capacitor was how much? C times V, Q equal to CV. And that CV charge went from VDD to ground. Therefore, total energy lost, CV times V, charge times the voltage across which the charge is transferred. So CV square. So that CV square energy is lost. But at what rate it is lost? CV square divided by the time period of the waveform. That means CV square times F. So CV square F is the power dissipation. So the moment you increase the C, definitely your energy power dissipation is going to be more, right? I will write those things down, but you can just, and what else? So energy dissipation is one, but regarding the waveform, what else do we see going to happen? Yes, regarding the waveform, anything else? Okay, you simulate and let us see what is the waveform coming. You may get a very bad waveform. So what is the difference? Is there any difference that you are seeing? Zoom into any one of them. Plot the input also. Any difference that you are seeing from the earlier case? Make the capacitor further higher. Make it say 20 femtofarad. Zoom into that one waveform, one or two periods. Yes. What is the difference? Any difference that you are noticing?
Rise time greater than fall time.
Sorry.
Rise time is greater than fall time.
Greater is fine. So greater, but apart from that, what else? So how will so overall, what is happening to rise time, fall time? Increasing, right? It's obvious that the rise time, fall time will go on increasing if your cap is more, because it is taking more time for the PMOS to charge the capacitor and taking more time for the NMOS to discharge the capacitor. So overall rise time, fall time will go on increasing if your cap is increasing. That is first thing. Now, that should be clear to everyone, right? So just go ahead and try to make it say 50 femtofarad. Now you will see that the waveform will become almost triangular because it is not even able to completely reach the VDD level within that time. Right, so it is not even able to reach the VDD. You can see that the PMOS is trying to charge, but it is not able to reach the VDD because the time is too short, current is cap is too large. It is not able to charge it completely. Right, so we are seeing the effect of larger load capacitor. Now, what can be done to improve this scenario? It is able to discharge, but it is not able to charge. What does that mean? If you allow it more time to charge, it will charge, right? So if you reduce the frequency, or that means if you increase the pulse width of the signal, it will charge, it will reach. Right now, the pulse width is too small, it is not able to reach. But now within this pulse width, if we want to still make it reach, what can be done? Yes.
We can change the
Anything?
duty cycle, like the time for which it is off, we can increase that and reduce the time for which it is on. The input
No,
voltage.
I'm saying that the waveform is as it is. What else can you do in the circuit so that it basically the cap is also given? Now, what can you do so that it is able to charge? Right now, we are seeing that the PMOS is. What do we conclude from here? So here, if I say the PMOS and NMOS, which one is stronger? That means which one is able to supply more current, or which is having more stronger on current.
So somehow, if we can change the effective resistance, which is looked by which the capacitance is looking, then maybe we can make it charge faster and like.
Don't think in terms of, yeah, impedance is, again, small signal impedance is one thing. That is a small signal parameter. So it is good to talk about small signal impedance in case of analog circuits. This is the digital circuit, and we talk about large signal resistance. So on resistance. So on resistance of which one is higher? So when the NMOS is high, the NMOS is on, it is having non-zero resistance, right? It is not zero resistance switch. When it is on, it will have some non-zero resistance. Likewise, when PMOS is on, it will have some non-zero resistance. When they are off, ideally, what do we say? Ideally, it should be cut off. It should have infinite resistance. But even in the case when the device is off, it is not ideally infinite resistance. It is having some finite resistance. It is very high, but still finite resistance. So ideally, an ideal switch, an ideal MOSFET will be having zero on resistance and infinite off resistance. That is an ideal MOSFET. Zero on resistance, infinite off resistance. But there is no ideal switch in the world. Every switch, every MOSFET will have non-zero on resistance, and it will have finite off resistance. So in this case, if I talk about on resistance of the MOSFET, which one is having supposedly higher on resistance, or which one is having PMOS is having, it seems like it is having higher on resistance because it is not able to charge fully. And as a result, the charging current is weaker. So in order to increase, in order to reduce that on resistance, if we reduce that on resistance, it will charge faster, it will be able to reach. So what can we do to reduce that on resistance?
Increase W.
Increase W. So make the W 1 micro for PMOS. Generally, yeah, just go ahead and simulate. So now you see at least it reached the VDD. So to some extent, it is able to reach. The waveform became symmetric once again. So both NMOS and PMOS now at least they are able to fully charge and discharge, right? So this is another important point. If you want to improve it further, both NMOS, PMOS, you may have to size it up further. If you increase both NMOS and PMOS, the waveforms will become further sharper, right? So because what is happening when you are having larger W, definitely your on current is more, the charging current is more, discharging current is more. Therefore, for a bigger load capacitor, it is able to charge and discharge faster. That is obvious, right? So nothing big deal. So if you want to make the waveform sharper, in this case, you can simply increase the PMOS and MOS W further. L, we can keep it minimum because whatever the minimum technology node, whatever the minimum L the technology node provides, we stick to that minimum L for digital circuits most of the time. So in this case, we are keeping the length minimum, but we want to improve the waveform, then we have to increase the W and L both so that it is able to improve the rise time fall time. So maybe you can go ahead and increase the both NMOS, PMOS. So NMOS, you can make it maybe right now it is 0.25, make it 1 micro. PMOS, you make it 3 micro. Before we do that, you can just simulate just plot the currents also, charging, discharging current, the PMOS source current and MOS drain current. Now you clearly see that the charging, discharging current for the PMOS and MOS are coming much more prominently at the rising and falling time. So NMOS current should be coming as a rising time or the rising edge, PMOS at the falling edge. And you can see the waveform with respect to the input, what is there. So now the output waveform I cannot see. Where is the output waveform? Yes. So now you can see when the input is going low, you're having the PMOS current, which is the M1 current. And when the output is going high, you're getting a big NMOS current. And as some of you mentioned, that it is remaining high for a longer duration because capacitor is big and the NMOS is charging and discharging the capacitor. It is taking longer time. So rather than being a very narrow spike, it is turning on and off for a larger duration. So that is expected because if your capacitor is large, it will consume more power. CV square F will be the power consumption because remember, CV square is the energy lost in charging and discharging the capacitor, and at what rate that energy is lost, CV square F. So that is the case. So now we can discuss. So you can go ahead and just so another thing is that the other spike that you're getting that is now smaller, right? So as compared to the main charging discharging current, the other spurious spikes that you were coming that is smaller because now the charging discharging current is much bigger. The capacitive coupling that was happening that is still contributing to some current, but that is much smaller in magnitude as compared to this main charging discharging current. Now you can go ahead and try to increase the sizes so that the waveform further improves. So what do we expect if we increase the W and W of NMOS as well as PMOS? What should we expect? That now the R on of the PMOS and NMOS both are getting reduced. The charging and discharging will become faster. As a result, the pulses of the current will become shorter because R on is less. But then the magnitude, the peak magnitude of the current will become bigger because the amount of charge you are putting on that cap is same, both cases, right? CV, that is the amount of charge, Q equal to CV. So the amount of charge is same. Only thing is now the R on you have reduced. As a result, the current will flow faster. It will charge the capacitor faster. Therefore, the magnitude of the current will go high. So right now you can see the peak current is coming around the 1 milliampere, right? The red one and blue one, the peak current around 1 milliampere. Now, if you increase the PMOS and MOS significantly, this peak will go up. It will go to 2 milliampere. So you can do that. Maybe you can just try to, you have already increased, it seems.
Yes, sir.
Yes. So as compared to the previous value, it will increase. So as compared smaller W case, it will, and the waveforms will become sharper. So you can see that the rise time fall time has become slightly better. You can increase further, maybe make them 6 micro, 2 micro, something like that. Now you can see it is again coming back to rectangular, rise and fall time is improving, and the peak current, you will see that it is almost reached 2 milliampere, right? So it is expected because you're having reduced R on, and as a result, it will charge faster. And power consumption point of view, if you see CV square F. So the F is remaining same, C is remaining same, V is also remaining same. So overall power consumption is likely, right now we are getting theoretically at least it should be more or less same for the output capacitor. The charging, discharging of the output capacitor, if you are only accounting for that, the power consumption is going to remain same. But what are we missing? Net power consumption of this circuit, are we missing anything? Can you plot the current of V1, the current going out of V1, gate voltage? So here, can you just zoom in to V1, any region of V1? So V1, just maybe you can remove other things so that it is clear. So you can see that there is a current pulse when the input signal is going down. There is a upgoing current pulse, and when the input signal is going up, there is a downgoing current pulse going into V1. So what does the direction mean? So he has plotted the current of the positive terminal of V1, right? So when he put the marker on the positive terminal of V1, it will show you the current at that terminal. When the current is entering into the positive terminal of V1, it will be shown as positive, because for that is the definition for most circuit components. Any current entering into that terminal will be shown positive. So a positive spike, this pink color waveform, the positive spike means the current is entering into V1. Negative spike means current is exiting from V1. That means it is flowing out of the positive terminal of V1. Now, how do we explain this? What is causing this current?
The source gate capacitive coupling.
Source to gate capacitive coupling. So what is that coupling doing?
Like when the input signal is going from high to low, then basically the current will flow from the VDD to the capacitor charging it. So because of this high frequency, the impedance, the CHG impedance between the gate and the source of this PMOS is quite low. So it's basically some current, there is some signal path from V2 to V1. So there is some current flowing from V2 to V1. As the V1 is going low and the V2 is at 1 volt, so there will be some current.
Yes. So effectively, what you can say, this would have been good if I could. I somehow forgot where is the annotation option. There is some option somewhere. Accessibility filter options is fine. There is. Anyway, so this is what this is pen. So can I do anything using pen? I don't think so. Anyways, right now I'm not able to locate the annotation option somewhere. I think as far as I remember, it should be there somewhere. So the thing is, what he mentioned is correct, that you ultimately have some parasitic capacitors in the MOSFET, right? The CGS, CGD. So what is the capacitance being faced by the V1? So if you look at the connection from gate of the M1 to source of the N1, there is a CGS of M1. Likewise, from gate of the M1 to the drain of the M1, there is CGD of M1. Likewise, from gate of the M2, the source of M2, there is CGS of M2, and gate of M2, the drain of M2, there is a CGD of M2. Overall, these capacitors, you can, at every point of the transient waveform, you can, if you assume that small signal behavior for different parts of the signal. Suppose the signal is rising up, for every small section, you emulate the small signal behavior. Overall, it's a large signal, but what I'm saying is the rising time, the rising section, you break it down into small portions and evaluate the small signal behavior. So you can apply Miller effect, right? Miller effect between gate and drain. So that CGD will get broken and you can apply that CGD between gate and source. So effectively, you can break down the CGD also and bring it in parallel with CGS of the PMOS and NMOS. Now, small signal point of view, the both sources, PMOS and NMOS sources, are at AC ground. VDD is also AC ground. So effectively, we can get a small signal capacitance between gate and AC ground, right? So CGD can be broken down into CGS. The effective Miller effect, you can bring that CGD in parallel with the CGS, and that CGS appears between gate and AC ground for every small increase in the gate voltage. So that means that you are having a effective capacitor between gate and the AC ground. And therefore, whenever the signal is going up, it is charging that effective capacitor. And when it is going down, it is discharging that capacitor. So this circuit is not only taking current from VDD, from V2, but it is also taking current from V1. That is also to be accounted for. The moment you are increasing the W by L of M1 and M2, when you are increasing the W, what is happening to that capacitor? When you increase the W of M1 and M2, what happens to that capacitor? How does that
Capacitance also
capacitor
increases.
depend? Sorry?
Capacitance also increases.
Capacitance increases because remember that the gate capacitance is CGS is equal to what? Approximately, it was proportional to W times L times the COX, right? Oxide COX capacitor. So the gate voltage, sorry, the gate dimension as it increases, W times L increases. As a result, the effective capacitance CGS also increases. So the moment you have increased the gate sizes, the MOSFET sizes, that means you have increased those capacitors. That means the current being provided by V1 will increase because now it has to charge bigger capacitor. The CGS has increased. As a result, the load capacitor for V1 has increased. As a result, now the power consumption because of V1 will increase. In an actual circuit, ultimately all these V1, V2, ultimately they will be coming from VDD because assume that this V1 is getting replaced by another inverter. Suppose there is another inverter before this first inverter that you have drawn. You replace the V1 by another inverter. Ultimately, the second inverter will be drawn by the first inverter. So that inverter is now playing the role of V1. For that inverter now, it has to supply a larger capacitor because this second inverter will be providing a load capacitor to the first inverter, and now it is charging and discharging a bigger capacitor effectively when you increase the M1 and M2. Therefore, the net power consumption of this circuit is not only given by the current provided by V1, but it is also going to be the current which is provided by V1. V1, V2 both need to be accounted for. So although we saw that the net power consumption CG square F because of C1 and V1, C1 and V2, that is remaining same, but the power consumption because of driving the gates of M1, M2, that is going up because your overall load capacitor for V1 is going up, right? So to do that, maybe we can try to replace V1. So what you can do is just stretch V1 backward and copy M1, M2, put another inverter between V1 and this first inverter. So you just copy this entire inverter, make another one, put it between V1 and this first inverter. These are very basic concepts. You should be very much aware of these things, at how the inverter characteristics is looking like, how the charging discharging is happening, where the power consumption is coming from, fundamental things. Anybody having problem, anything not clear, don't hesitate. Somehow I'm not able to annotate because if I was able to annotate, some things would be easier to explain. Yes, so maybe you can remove the cap, you can remove from the first stage. So all these extra things, the grounds and the cap, all those things you can remove. All right. So no, that will be connected to the output of the first inverter.
Is this all right, sir?
Yes. So now you can see that uh, the first inverter is driving the next inverter, second inverter, and therefore now the gate of the second inverter will be charged and discharged by the first inverter. That means M3 and M4 are now charging the gate of M1 and M2. And likewise, uh, in a big circuit, there will be several stages, several gates, and one gate will be driving another gate. Now, what you can do is you can plot the waveform of both inverters, the first inverter output, second inverter output. You can simulate it for smaller duration, so long duration is not required. But anyway, so yeah, so you can see now you can also plot the input overall input signal. Zoom in, show two pulses at least. So you can see after two inverters, the signal will be non-inverted. So your input signal is the red one, and the green one is the final output. And definitely you can see there is some delay, right? So how do we define the delay? Delay between the red curve and the green curve will be measured from the midpoint. So midpoint of the red curve, that means the rising edge of the red curve and rising edge of the green curve. The distance between them will be the delay overall. So can you put a marker at this point and measure the delay? What is the delay between the rising edge of the red curve, midpoint, and midpoint of the green curve? There is a marker, I think, in the
Here is the marker option, sir.
can you just I think in some corner it shows the value. So if you click at any point, uh, it will show the value. So and there should be, I mean, this marker that you're moving, it should show some in some corner, it should be showing the value. So I'm not able to see the full screen, but it shows the value in some corner. Are you able to see anywhere? Yeah, so somehow this pop-up that is coming, this pop-up also I'm not able to see the whole window. I'm seeing only some corner. So I think everybody is having the same thing. So maybe you can just compare the midpoints of the green curve and the rising edge of the green curve, rising edge of the red curve. So here we can see rising edge of the red midpoint, not the starting point, midpoint. If you are not able to get because the red curve is very sharp, you will not get the midpoint easily. So you need to zoom in a little bit, or maybe you need to provide larger rise time for the red curve. Yeah, so go to the midpoint. Yeah, so this is 3.0028 nanosecond, and the other one midpoint, close to midpoint where it is VDD by 2. Go to that point where it is VDD by 2. Yes, so here it is the second point is coming around. So this one is which one? So called cursor 1, cursor 2. Cursor 1 I can see is 0.3.008. Sorry, 3.0028. Cursor 2 value I cannot see somehow. Can you tell me what is the cursor 2 value?
3.045.
3.045. So almost 45 picosecond. That means the delay between the red curve and the green curve, the difference between the rising edges, midpoint, is around 45 picosecond. That means the delay of two stages here, we are getting around 45 picosecond. So in this node, 45 nanometer CMOS node, we are getting, for this device dimension, we are getting a delay of around 45 picosecond for the two stages. Again, this delay depends upon several factors. Right now, can you tell me which are the factors on which this delay will depend? We have already seen certain things, but the overall delay between the input and the output will depend upon what factors? Yes, anybody? So you saw how to measure the delay, right? So that part you should be able to do. The delay between input signal, output signal, using that marker, uh, using that cursor, basically, you can calculate. Yes, anybody would like to mention, like, what are the factors on which this delay will depend? We have already seen all this simulation, so we should have all the answer that on what factors this delay is dependent.
Sir, the width of the MOS we are using, that is, which is controlling the turn on resistance, and then the capacitor value which we are putting at the end.
Yes, so definitely the capacitor value and the sizes, because sizes are not only controlling the because capacitor is only at the output, right? So the net delay will depend upon capacitor, that is true, but the capacitor is being driven only by the second stage. First stage is driving what? For first stage, what is the load capacitor? Yes, anybody? For the first stage, what is the load capacitor effectively?
Sir, the capacitor that appearing at the gate
Gate
of the
source
circuit.
gate source
Sorry?
capacitance of the NMOS and
Yes, so gate to source capacitor for the NMOS and the PMOS
and also that of like of the first stage and also the drain source capacitance of the first stage NMOS.
in the MOSFET model, have you read any drain to source capacitor? Yes, in the MOSFET model, is there any drain to source capacitor, small signal model? You have forgotten the small signal model of MOSFET.
So there is no drain source capacity.
So what are the small signal capacitance is present in this MOSFET?
Gate to drain capacitance will be also a factor determining the time.
So for the second stage, if I look at the output of the first stage, what are the capacitors coming into picture? That is what I'm asking.
So gate to source capacitance of M2.
And
Gate to source
yes,
capacitance of M1 and M2 and gate to drain capacitance of M1 and M2.
anything else?
Drain to body capacitance of M3 M4.
Yes, drain to body capacitance, because the body terminal of M3 and M4 is VDD and ground. So from drain to the body, CDB of M3 and M4 will also come between that output node of the first inverter and AC ground. So the drain to body capacitor of M3 and M4. Anything else? The drain to gate capacitance of M3 M4 will also play some role. You can again assume that there's going to be some Miller effect kind of thing between the gate and drain capacitor. The CGD of M3 M4 will play some minor role as well. So these are the capacitance which are contributing to the net load capacitor or effective load capacitor at the output of the first inverter. So when you are increasing the size of all these transistors, you are not only reducing the on resistance, you are also increasing the capacitor value at the output of the first stage and also output of the second stage. Because second stage output, although we have a big capacitor of 50 femtofarad, but if you keep on increasing the MOSFET sizes, it will eventually start increasing the capacitor also. So the net capacitor at the output of the first inverter as well as second inverter will go on increasing if you go on increasing the W by W, and right now we are keeping the L minimum. We are not increasing the L. For digital circuits, we want fast operation, so we keep the L minimum. So in this case, if you go on increasing the W and for the first as well as second inverter, it is going to increase the effective capacitor at the output of the first inverter as well as second inverter. And as a result, what will happen? Your delay will not improve because R on is reducing, but your capacitance is also increasing. So the delay will stop improving. What will happen to the capacitor? Capacitor is increasing. As a result, the net energy consumed by the circuit that will go on increasing because the capacitor is continuously increasing. You are charging and discharging the capacitor to VDD to ground, VDD to ground. And therefore, as you keep on increasing the sizes, the energy will go on increasing, power will go on increasing because the net capacitor is increasing. So what will happen initially when you start with very small sizes, initially the R-on is high because the MOSFET dimensions are low. But now, as you gradually increase the W of the MOSFETs, R-on is reducing. Therefore, it will improve the speed. But as you go on increasing further and further, the C will also go on increasing because the parasitic capacitance will start contributing to the overall capacitor. Therefore, although you are going on reducing the R on by increasing the W, the C is also going on increasing. As a result, at certain point of time, that R and C improve, the R will reduce, but C will increase. As a result, it will cancel out the effect and will no longer give you higher speed. Speed improvement, rise time, fall time improvement will stop. Right? That phenomena also we should be aware of. Any question before before we conclude this? There are a lot of other details regarding the inverter that we need to discuss, but this simulation point of view, at least delay calculation, rise time, fall time calculation, even power consumption, whatever we are doing right now, we can calculate. I think there's a calculator option. You can, if you are, so in this case, if you want to calculate the power consumption, as I told you, there are two voltage sources being used, V2 and V1. So power consumption because of both should be taken into account. And I explained why, how the V1 is contributing to power consumption. I hope that is clear to all of you. Any doubt in that? Both V1 and V2 are contributing to power consumption. Is that understandable to all of you? Any doubt in that?
Sir, I had one question.
Sorry?
Sir, this power supply voltage. So this power supply voltage will play some role in the delay.
Yes. Why it will play a role?
Sir, that's what I wanted to ask because sir, actually I swept the V2 from sir, from 0.5 to 1.
No, you
1.2
answer. I
volt.
gave you the answer. Yes, it will play a role. So you give me the answer why it will play a role. Very simple. Why it will play a role? Why power supply will play a role in delay? You asked whether the power supply is going to play a role in delay. I said yes. What is the reason? Anybody? Very simple.
So the more the power supply, more the charge needs to be deposited in the capacitor. So more current needs to be.
Okay, that is not so correct. Anybody else? So what you are, according to this answer, what will happen if you have higher supply voltage? You are trying to deposit more charge on the capacitor, and therefore the delay should increase. That's what you are assuming.
Yes, sir.
Which is not true. What else? Means anybody else?
So actually, I saw the reverse happen. Like if we increase, then the delay decreases.
Why will it decrease? Why will it decrease? I already gave you the answer. Yes, it will decrease. If you increase the supply voltage to a certain extent, it will decrease. What if you reduce the supply voltage, the delay will increase. Conceptually, one person said that, okay, we are reducing the supply voltage, you are depositing less charge on the capacitor, therefore delay should reduce. But I'm saying no. If you reduce the supply voltage, delay will increase. Why? Anybody? Yes, anybody quickly? Nobody. I hope you're able to understand the discussions, right? So anybody can answer like why the delay will increase if you reduce supply voltage, despite the fact that reducing supply voltage means that we are charging the capacitor lesser. We have to deposit lesser charge. But why will the delay increase then?
Sir, one thing maybe that if I increase the supply voltage, then my drain current will increase, right? So if my drain current increases, then it will take less time to charge the capacitor, which I have at the load.
Yes. So the question is, which one is stronger? If I reduce the supply voltage, which one is stronger? The net charge stored on the capacitor is reducing linearly. That is one. But then the current
But
will
my
reduce
current is increasing square. Current will increase in
square, right?
square.
It will square. And then once if you go on reducing the voltage further, the transistors will enter into subthreshold region. There it will reduce exponentially. So although
Yes.
the charge on the capacitor is reducing, the total charge that you need to deposit is reducing. But in the super threshold region, as long as the gate voltage is greater than VT, the VDD is keeping the transistor in super threshold. In that case, there is a square dependency, and as a result, the current is reducing faster. And when the VDD is becoming too small, and then you start operating in sub-threshold, we will discuss about sub-threshold operation in more detail. So that is, when you are having a on voltage lower than VT or close to VT. In that case, the MOSFET equation becomes exponential. We don't have square law any longer. We will discuss all that. So in that case, the reduction in current will become exponential. So either it is reducing by square law or by exponential. Therefore, the delay will increase. So all of you have studied this sub-threshold region MOSFET operation, exponential equation, etc. EC people?
Yes, sir.
Okay, E people might not have. Any E people, have you studied this sub-threshold MOSFET equation, current equation?
No, sir.
Okay, so I will cover that briefly. I think in some of my lectures I might have done it. If I find it, I will give you. Otherwise, I will cover it. So any other question by anyone? So just check whether there is any average calculator. There is a calculator which can calculate average of waveforms. So can you find anything? Just check. I'm not able to see the whole window. I don't know. There is some anomaly which is not letting me see the whole window. So average of the waveform can be calculated. So if you want to calculate the power dissipation, we can calculate the average of the current being sunk. Anyway, that part I will see later. So any other question before we conclude today's discussion? I will give you some more steps in this assignment. So far, whatever we have done, you should try to, emulate and complete. And I will give you some more instructions related to this particular assignment so that you can simulate and understand things better. Anything else before we conclude? Inverters, understanding the fundamentals, operations, transient characteristics, power consumption, speed, sizing effect, all these are extremely important fundamental things. You should be very comfortable with this. Start getting comfortable with this. Any question before we conclude? So always we can derive equations and try to these rise time, fall time equations, current equations, but I'm not doing all the derivation because it's an accelerated course. But conceptually, you should understand what is happening. It's not difficult to understand. And these things should become very, very clear. Means it should be at your fingertips. You should understand what is happening. At each circuit node, what is happening, what is the capacitor at this node, what is the charging, discharging current at that node, what is the effect of sizing, what is the delay, how do you calculate delay, rise time, fall time. power consumption, all those effects you should understand. Anything else? If you don't have anything else, I will conclude and I will give you some more extended steps in this assignment.
Sir,
Yes.
I missed the initial part of the discussion a little bit. So I had this question ki, when we did not have the two stage of inverters, when we had the single stage, and if we did not have any external capacitor connected at the output node, that time also the current waveform that we obtained, that it was in form of the like pulses. So can you like explain why it is in terms of like what is it charging that time when there was no external capacitance connected?
So that answer you should give me, because just now we also discussed what is the net capacitance at the output. That we discussed yesterday also, I mean, in the previous session also.
So in terms,
What is the
in
net
terms of
capacitance at the output?
the parasitic capacitances.
What are those parasitic capacitances? Which transistors are contributing to the parasitic capacitances at the output node?
So both the CGD and the CGS of both the NMOS and the PMOS, the parts of them due to the mirror effect that we saw.
Yes. So then what is the question? That gives you the answer, right? So there is a net capacitance.
So
Even if you don't
okay,
have that, then there is a capacitance because of the parasitics.
okay, so that is included in the model itself.
Yes.
Okay, no, okay, sir.
MOSFET model has all those parasitic capacitances. If you look at the model, if you just look at the text file, you will find some of the capacitor parameter mentioned.
Sir, one more thing. I wanted to confirm this, that if we simulate this thing without using the external capacitor, then it does not, the changing of width will not give much effect on the delay, right? Because the capacitances, the parasitic capacitances are very small. Is that the reason? Because I simulated it without the capacitor and there was no contribution to the delay. The changing of width did not contribute much to the change of delay.
Just because there you don't have the first of all delay will be very small, and then LT spice, either you have to increase the time resolution so that it can capture the delay more accurately. And second is that if you don't have parasitic, you don't have load capacitor, then you have both the factors. Increasing the W is reducing the R on, but increasing the cap. As a result, it is kind of cancelling the effect of each other. Is that clear?
Yes, sir.
Any other question?
Sir,
Yes.
hello.
Yes, tell me. I can hear
Sir,
you.
will there be any role? Sir, will there be any role of probe capacitor as well? Like when we are not connecting any load capacitor separately, but when we are measuring, there will be some probe capacitor.
No, in this simulation, there is no probe capacitor. Whatever probe you put is ideal. In actual circuits testing, yes. Yes, in actual circuit, when you're testing, yes, probe has effect. Its impedance, capacitance matters. It will load the circuit. Here, whatever probe you use, ideal probe. Here in the simulation, it will not have any effect. Any other question? Okay, so let us close for today. I will give you some more steps to be simulation, and gradually we will increase the duration of engagement also. So let's continue further. Any doubt? Any other thing not clear? Last chance for today. I will try to see how to annotate, because if simulation this discussion is going on, it is good to be able to annotate. That helps in understanding and better discussion. I will try to figure out what is the way. Anyway, so if you don't have any other discussion, let us conclude for today. Thank you. I think recording has been done. Stop.